But first, on this lovely day, what we're going to do is look at something called measures of spread. So our goal for today is to understand two of the most common measures of spread, variance and standard deviation. So by way of warm-up, we see that we've got two graphs that include the sort of like a frequency table of members of two women's basketball teams. So here we have the Dolphins spread out fairly nicely. We have the Sweet Peppers who are tightly packed in there. So as we look at this, what is the main difference between the two plots from just looking at them? So the main difference is about grouping. Spread out versus concentration. So what's the mean, median, mode, and the 5-number summary? So by the way, median is part of the 5-number summary, so that's redundant, so I apologize for that. And then the IQR is derived from the 5-number summary. So we see both of these have the same mean. For our purposes, let's skip the median and just do the 5-number summary because that's in order also. So just to refresh, the 5-number summary for the Dolphins is right here. 70 is the min, 80 is the max, and here's Q1, Q2, and Q3. Therefore, the IQR is 79 minus 71 to give me 8. We see, of course, that the means are the exact same. Our minimum and maximums are the same. Now, our medians are different. Medians and Q1 and Q3 are different than over here, but pretty darn close. The medians are almost exactly the same. And then lastly, the IQR, this one here is 75 minus 75. 75 minus 75, which means the IQR is 0. So as we see, because our means are the same and our medians are close to the same, we need something that's a little more fine-tuned to help talk about the distribution differences. Now, clearly the IQR helps us out a little bit with that because the IQR tells me that the data is spread out. 50% of my data falls in between, 8 inches. But 50% of my data is stacked on top of itself right there. So with that in mind, we know that there is something to do with the spread is different because of those two numbers. But today what we're going to look at is something called the variance and standard deviation, which will help us understand spread a little bit more. All right, so as we saw earlier, we saw that up here, the mean and the median weren't very helpful because it just wasn't enough information, right? The 75s were the same, but up here were radically different. It was the median were very close to being the same, 75 and 74.5. So again, it didn't tell me about the fact that this is really squashed together, the data is, with a little wings, and this one's just kind of flat all the way across. So this one's evenly distributed for the most part. Okay, so we need something that's a little bit more sensitive to attack that. So we're going to look at two kinds, and this first has to do with what's called the population. When we're talking about the population, we're talking about the entire group, like the population of this class, every single person. Or if I can talk to every single person in the United States, I'm looking at the population, okay? But practically speaking, we can't always talk about population. We sometimes have to talk about sample. And so that's what we're going to look at in the next few after this. But first, we're going to start off with population, if you have information about every person. So when talking about population, the mean uses this symbol, and it's a Greek symbol, and it's pronounced mu or mu, depending on where you're from. And this is how you draw it. You just draw it like this, kind of like a fancy M with a longer tail. Okay, just to draw that again, long, then come up like a U, and then down like that. So that's the Greek letter mu, pronounced mu, or sometimes M-Y-U, pronounced like that. Mu or mu. And this is mean, of course, and it's just, like we said before, it's your average. Okay? So we'll get to it in a second. Deviation. What is deviation? Deviation is how far away any particular number is from the average. In this case, is from the mean. So how far away one term is from mu, or the mean. Okay, next big operation that we're going to do is that we're going to take that deviation, each one of them, and we're going to square them. We're going to square them. I'm going to tell you why we square it for two reasons. Why we square it for two reasons. Number one, it positivizes, that's not a real word, but positivizes, oh, bless you. It positivizes all my numbers. In a moment when we walk through the process here, we're going to see that this is pretty important. And number two, it makes large deviations larger. That means if something is further away from the mean, so a further away, either a positive distance or a negative distance, what it does is we square that, so it increases its influence on things. Okay, the next step we're going to do is we're going to find the variance, and the variance is defined as this. If we walk through this step by step, remember this is sum, this right here is the deviation, and I'm squaring it. So I find all the squares of the deviations, I add them all together, and divide by n. So what does that mean? It is the average of the square of deviation, the squares of deviation. In a moment, we'll see graphically how this works out. It sounds really complicated, but it's actually almost exactly the same as the distance formula in geometry. All right, finally, so we call this one sigma. And again, sorry, so this is the lowercase s. So this is capital case S in Greek. That's uppercase sigma. And this is the lowercase sigma. So these two are the same letter. They're just different lowercase and uppercase. So variance is sigma squared. And down here, standard deviation is just simply sigma, no square. So how do we get it? It's the square root of the variance. So this right here is a modified version of something like this here, where we're just stacking things up. This is 170. There are two 72s here, 180. So this one has 1, 5, 1, 7, 2 8s, and a 10, okay, in this data set. So I'm going to graphically think about and show you what happens. Okay, the mean is just what's the average of all these numbers. So the mean is going to be somewhere about here. Somewhere about here, 7.6, I think. So my average, my mean, is going to be 7.6 here. Okay, so graphically speaking, what is deviation? Deviation is this. How far away is each of these? Now, it's not perfectly that, because there's positive and negative, right? Because I'm in the positive direction this way, I'm in a negative direction this way, I'm in a positive direction this way. So each of the deviations can have a positive or a negative, okay? I'm not going to run through the actual calculations here, but what we will do is walk through the graphical. So clearly, these ones over here are going to be positive. We don't need to write that. I'm just showing you positive. This one's negative. This one's negative. Okay. Now, the process that we're doing geometrically looks like this. And you don't have to remember this, but as I was thinking through this helped me visualize a little bit what was going on. So the yellow is the deviation. Now, the square of the deviation does this. The square of the deviation creates a square of each line segment here. So we've got a little bit of a small square there, a medium-sized square there, a larger square here, and a rinky-dinky square there, like that. Okay, so now we've got all these areas now represented. Again, very much like Pythagorean theorem. Okay, Now, what the variance does, so the square of the deviation creates these squares, regions. The variance means I'm going to add them all up and divide. Why? Because I'm going to take essentially the average square size. It's the average square size. So that's what we're doing there. We add them all up. We find the average. And when we do that, notice that we'll end up with something this big, right? We melt them all up and then cut it into equal parts, and we end up with something like this. So that becomes my average, because this is the sum divided by the n, which is what that is. And now, the very last thing we do is, when you take the square root, that means what's the length of one of the sides, that is my standard deviation. So, in the end, we have standard deviation after, essentially, we find the side length of the average size square. Blah, 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 blah. Okay, but let's take a gander at this data here. We already calculated from the dolphin data previously, we already calculated that the mean is 75, okay? So by hand, how do we calculate the standard deviation? Well, we have to do all of this. So what's the deviation? First off, what's the deviation? So I take the term number itself, the 70, and I subtract from that mu, the average. So, and then I get a number here. In this case, it's 5. So I'm going to repeat that process. 71 minus 75. And forgive me, I forgot a negative there. I get a negative 4. Then again, I repeat that process. And we can actually do this in our head, so feel free to not write the sums the whole time. 73 minus 75 is negative 2, so we get negative 1. We get a 0. Here we get a 3, a 4, a 4, and a 5. If we were to do a quick check here, and just to add these all up, we expect all these to add up to something nice. In fact, we expect them all to add up to 0. Why is that? Because that's exactly what average means. Average means you've got a bunch of stuff that's above, a bunch of stuff that's below, and something that's exactly the mean, the in-between, not middle, but the average of everything adds up to 0 here. So look at this. The 5 cancels with that 5. The 4s here drop out. The 2, negative 2 and the 1 drop out with that 3. So we end up here with the sum being 0. So notice that if I were to try to find the average of the standard deviation, or excuse me, the average of the deviations, it doesn't help me. Why? Because 0 divided by any number is always 0. Okay, so next, we're going to square everything. So what this does is, like we said before, it does two things. It positivizes all of these numbers, kind of like absolute value would, but it also makes this 5 and this 5 more valuable. And it makes this 1 not so valuable. Okay, so now we just square everything. So just attack, kill, destroy that. 25 here, 16 here, 16 here, 4, 1, 0, 9, 16, 16, and 25. And all this adds up to 128. Now to find the average, now this is called the variance. When we do that, all we do is take this and divide by the total number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 members on the team. So the 128 divided by 10 clearly is 12.8. Now the last thing we do is take the square root, and that is called the standard deviation. And I am going to change the symbol here to approximately equal to 3.58. Sorry, 3.58. What does it mean? Standard deviations now mean it talks about what type of spread I have in terms of the data. The data spreads out pretty well. So just to give you a heads up, as if your sigma is small, then that means the spread is tight. Everything's closely related. But if you have a larger sigma, that means you're spread out. Spread out more, okay? So if I were to look at this here, and we know that the mean is 75, right there. Well, nearly 3.5 is my standard deviation. 1, 2, 3.5 there. So this is my sigma. 1, 2, 3.5 there. So my standard deviation here says that it's spread out. The data is spread out. As we look at this one, which has a standard deviation of 2.28, because that's the sweet peppers standard deviation, sweet peppers has an approximate of 2.28, while the dolphins had an approximate of 3.58. Because of that, we see that this number here tells me the data is more tight. Tightly packed up or something. So, as we said earlier, we talked about population, that we did a population standard deviation. And as we look at this, we see that this one up here is about population. That is, like I said before, when you know the whole group. And here we divide by n. That's the number of people. But some mathematicians who are smarter than I and have looked at data a lot more decided, and other people agreed with them, that when we're dealing with a sample group, just a fraction of the population, not the whole thing, then instead of dividing by n, we're going to divide by n minus 1. I honestly can't tell you why that's the case, but that is what was decided. So, besides that, we also have a few other things. Number one, for the entire population, we use the Greek letter sigma for lowercase sigma, sigma squared for variance, and sigma for standard deviation. But down here, we use a lowercase s for that when it's just a sample. Lowercase s for sample. So this means everybody. This means a sample. And instead of the Greek letter mu, like up here, instead of the Greek letter mu, we're going to use the x bar here for that. In this example, according to the United States Department of Agriculture, 10 to 20 earthworms per cubic foot is a sign of healthy soil. So, Mr. Green checked the soil in his garden by digging 7 1 cubic foot holes. And he counted the earthworms. He doesn't have to do them all together, by the way, and you don't have to draw this out. But if you did want to take a sample of your yard, what you would do is just, dig a hole here, dig a hole here, 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 and here, just like that, and then count the worms in there. So that gives us a sample of his whole yard. Okay? Then, and he found the following counts. In one hole, he found 4, then a 23, a 15, a 10, 8, 12, and 18. So notice this is not the entire yard. He didn't dig up the whole yard and then count it out. And you can't. If you dig up the whole yard, you don't have a yard. So, by the way, this is also how a lot of archaeology is done. So instead of digging up an entire archaeological site, because you don't want to ruin things, sometimes they just dig up in little areas to try to figure out how densely populated something was, or other pieces of data. So we want to calculate the variances and standard deviations of the earthworm per cubic foot. And in the end, we can actually say, well, so is this kind of healthy? And how big of a spread is this? So we can do this by hand, or we can do this by calculator. So after we plug everything in, we see that our sample our standard deviation. My S's look like 5s. I'm so sorry. I got to try to fix that one. All right. My S is approximately 6.4, which means my variance is going to be that squared. So when we square that, we get 40.8.